Yeah, pretty much. Yeah, so we have like someone replacing.
All right. Evening, everyone. Last time we left off, I was going over some motion diagrams. This page was filled with arrows. And if you want to see more exactly how I filled that up, it just sort of erased it right now. Basically, this is your way of sort of in your head visualizing what's happening with anything that's moving. In this chapter, it's in one dimension, so things moving in a straight line. It could either be left, right. I had this big, long track out here last time. And I was talking about a car that was rolling back and forth at a constant velocity. So I gave it a little push, and it moved constant velocity. That sort of represents this hockey puck, the top left. Then we had like a baseball example. This is something that is experiencing an acceleration. So I give it a, very quick bit of velocity right at the bottom, and it's experiencing a constant downward acceleration. So the acceleration, pointing downward, is opposite that initial velocity. So velocity up, acceleration down, they're countering one another, so it's changing in a sort of a reducing way. Then you look on the right side, that's the point where the ball is starting to fall down. It is now creating a velocity downward. The acceleration continues to be downward. And since they are both pointing in the same direction, they sort of add to one another. Then we had sort of a mixture of the two on the bottom with a sort of car, starting from a rest, speeding up to a consistent, constant velocity in the middle, and then we had it slowing down. So its velocity is that way, but it wants to change its velocity, so its acceleration is opposing. So it will stop. All right. That sort of leads into talking about how can we describe all of these motions a bit more clearly. Maybe we don't want to draw a picture all the time. Maybe we want to predict something very exact. We need to use equations. So that will lead into us developing the kinematic equations. And for all of the kinematic equations that we see today, or pretty much all throughout the semester, they're going to be dealing with something under a constant acceleration. So, say we have that car. In fact, let me go get a little car real quick. Say we have a car. It's moving with a specific initial velocity. It's actually going already. So it's moving at a constant velocity. It's going to remain this way forever. Now there's a little bit of friction, so it slows down. So we have this constant velocity. It's just a value and a direction. So it's a vector. But then we want to accelerate this object. Instead of it going at this speed forever, we want to change its velocity. So say it starts with this initial velocity, and we want to change it to this velocity. Take the thing. Okay, so that means there's a small moment in there where I have to change its velocity from this to this. So that small change in velocity, remember what acceleration means. That change in velocity is going to be sort of shown like this. We can write it like we have x. So we want to find the velocity. Well, that's just equal to whatever it starts out as. Its initial velocity, so that's v sub naught. That's just a small little 0. That's me sort of putting a tag on it, so I could keep track of where that specific one is. And let me do this for later. So we're going to get onto this section, maybe in the last part of the day. I want to make sure I'm sort of saying still moving in that straight line. So I'm also going to sort of label it v sub naught x. So its initial velocity in this, horizontal one-dimensional case. So if I had that car, its initial velocity was this, and I don't change it in any way, then its final velocity is also that. They're the same. We want to add a slight tweak to it. So we're adding some sort of change to velocity. Which is an acceleration. So let me rewrite this. Plus this change in acceleration, this change in velocity, which is an acceleration for a small amount of time. And I could say t, or I could say, it might be more correct if I say delta t. So let me do that. Okay, so we have this way of, determining velocities. Say we're given, it accelerates with this, size and direction, accelerates that way for 10 seconds, and it starts from a rest. We're able to find a final velocity. So just given like, how much of a push, and how long we're pushing, we can see how the velocity will change. And this is kind of something that's brought up. I went over instantaneous versus average, like velocity. Well, it's the same thing with the acceleration. But in this case, where we're only looking at constant acceleration, so the average value will be the same as the instantaneous value. So all of these kinematic equations I'll go over, I'm just going to say average, and so I'm just going to call it that's just the acceleration, since we're going to have enough going on in these equations already. So instead of being like acceleration in this little bit and acceleration in that little bit as it changes over time, we're just considering it all the same. Right. Nice. All right. So now we'll get into where these kinematic equations will come from. Oop. There it is. Okay. So, this whole beginning of the semester, this whole intro bit is just a nice sort of thorough, first it starts as like a math prep. And then it goes into just sort of some reasoning. I say, this thing's moving. If nothing happens to it, then I can say at a later time it's still going to be moving at that rate. So it's sort of a, reasoning sort of a assignment we're doing right now. That's the case I did with that car. So now we're going to go back to, I had a bunch of graphs last time. There's sort of a reason for that, because the graphs make it easy to do, make all of this sort of physics easy to do without necessarily needing to use calculus. So I'm just going to hopefully explain by using these sort of small little graphs. So if we had last time, I said if you were moving at a, or if you already had lab, if you are moving at a constant velocity, the velocity is the same value, and so it will be represented as a straight line. That's this blue line up here on the top. I need to label my axes, so let's do that. So this is velocity versus time. And I'm going to say that I'm only considering two sort of, pieces. I'm not starting right when, the thing starts going. I'm just going to say these two dotted lines. That first little bit we call first time, second little bit, second time. And this blue line I'm going to call the initial velocity. Okay, and something that will be helpful to us is we can find the displacement by finding the area under the curve in the specific zone we want to look for. So we want to find how far that car went. We could simply graph it, find the area. Finding the area of a rectangle is fairly easy. So I could say this is, delta t. Area of that is just delta t times v naught. So side times base. Okay. So this will be a, let me sort of highlight, the one on the top is a positive area. Let me use like a different color. So this is a positive area. We could also have a negative velocity, and since velocity is a vector, this is merely just saying which direction the thing is going. So wherever we call 0, if I call 0 right here, everything over there is going to be positive, everything over there is negative. But I could also call like this position the origin at 0. So it always depends on the problem. Okay. And the bottom one, that is a negative area. And I'll just say, I'll sort of summarize. Area in the curve, yeah, I already have that. So we have another way of showing that the displacement, delta x, is the area. So the V naught times delta x. So I've already sort of put this up once, but now you can see it as, one side of the rectangle times the other side of the rectangle. Just sort of showing I can do this with just shapes. All right, that will make it easy for me to explain this next part. So that was going to be one of the kinematic equations. I'm going to rewrite them all at the end. Let's say we don't have a constant velocity. Let's say we have a car. Let me make the axes first. This is velocity versus time. What is this showing? What is the car doing in this case? It's accelerating. How is it accelerating?
In a positive direction.
A positive direction. So, yeah.
Did you run on the board?
Not yet.
Oh.
I labeled them.
Oh, okay.
Right. So what this graph is showing is that at one moment in time, it's moving so fast. After just a little bit longer, it's moving even faster. So it's something that is accelerating, getting faster and faster over time. Let's look at two specific, regions. Maybe I'll just make some random, points. I'm going to say right here at T1 and right here at T2. So I said earlier that the area under the curve can tell me the displacement. But if this, car is accelerating, getting faster and faster, that line is not as easy to find the area underneath. So how do we do that? Well, an easy way is to break it up into things that we can manage. So I sort of have these zones. Let's make a couple more zones that are easy. So I'm going to put these two new dotted lines. That's me just sort of splitting it up just because I can. And so we have, let's call this portion down here, we'll call this V1, and this one up here, V2. So at one point, it's going slow. At another point, it's going much quicker. But also, me sort of splitting this up makes some two nice shapes to find the area of, right? So what kind of shapes? We have a bottom, it's a nice big rectangle. We already know how to find the area of that. So we already know how to find the area of all of this. Right? It's one side times the other side. What's left? We need to find the area of that triangle. And now I need to be, more specific. I'll write it out. So this will be so we have final velocity and initial velocity. So this whole length right here is delta V. That's how much the object has changed its velocity. And I've also, or I've already related delta V to acceleration. Like that. So I'm sort of developing, just through these basic shapes, a way to create some kinematic equations. Now, for something complex, or a little bit more complex like this, I will end up with a kinematic equation that looks like this. So it's just basically how far, the whole goal of this is to say, starts at a certain speed, and then it's going to accelerate. Where's the thing going to be? Where's the displacement? Where's it going to go? How do I track this thing? So the displacement is equal to just adding up the area underneath the curve. We have that nice little rectangle. And in this case, I have it as 1 and 2. That's fine. E1. So one side of the rectangle times the other. And then we have to add that other bit. What's the area of a triangle? What's the area of a right triangle? So in this case, it's going to be 1/2 base times height. And the base down here is delta t. So we're ending up with a form that looks like this: 1/2 delta t times this. Okay. All right. So this is going to be another kinematic equation to help us figure out how to track something that's moving. I can sort of put up, I'll just some key points. Add up the area of each section. All right. So I'd say from this point, a lot of the other kinematic equations I'll put up in a minute are just going to be sort of from this. I'm just saying area under the curve, and maybe like taking one form, putting in the other. I think, I just sort of bore you guys, and I'd rather do some examples later on. So let's go to the, big list that I have written out. So with these kinematic equations, you can figure out nearly how anything will move. You can find velocity, you can find accelerations, you can find how long something has been moving, or final or initial velocities. The problem is, I'm just going to put all of them up. I've gone over the first two. These last two are just sort of, or I guess that third one is me sort of like plugging one thing into another. The thing is, knowing which one to use is up to you guys. So whatever the problem's asking, you're going to have this list, and you have to decide which one to use. I'll sort of write down what each one is kind of good for. That first one, what is not in the first one, the top? What's variable? Position, or x. So I'd say that first one is good if you're not interested in figuring out distances or locations, where the thing is. What is in it is, velocity, acceleration, and time. There's 3 variables. 4 variables. So if you have at least 3 of those 4, you can find the third one. Fourth one. So I would say if you're not interested in position, then that might, sort of bring up a thought. That second one has all of them in it. It has 5 variables in it. Why can't I just use that one always? It looks like it's the most, versatile, the most, hefty. The problem is, sometimes you might not know all of these variables. There are 5 variables: position, velocity, and acceleration, and time. The problem, or maybe you out in the real world, you won't always know how far a thing has gone. Maybe you're not able to measure a distance. Maybe you're not able to measure something's initial velocity. So that's v naught x right there. So even though it's useful, you might not have all of the terms. I will say useful if you know four of 5 variables. Okay, we're just going one by one. What's not in the third one? Time. Maybe I want to know how far something went. Accelerations I might be given. Velocities. I just don't care, when or how long it took. It already happened. I don't care how long, at specific times. If I don't care about time, if I don't have time, or if you don't care about the time variable, or the bottom one, that one can sort of be written, one more step. So I have the average velocity is, I just pick 2 points, one and the other. It's just the average. Pretty, simple. There's also, I can use this form. You remember what, delta x equals v delta t. I can use that, and I can sort of modify that average velocity formula. So what this one will look like is, so there's secretly 5 kinematic equations. All right. Once you sort of, do some, practice problems, you're able to maybe pick up on when and where you need to use which one. That's pretty much, I want to say, like the whole class, because this is one dimension, in the next chapter, we go over 2 dimensions, and we're still going to use these. And then in probably like a month, actually no, in a couple weeks, we'll go over rotation, things that spin, and it's the same things. And then what else? I think there's maybe one more, but we're always going to be using these types of equations. So if you can understand these, you know what they're asking, that's, this class is almost done for you. Okay. So, let's see. No. We'll do an example of some constant acceleration. So you're driving on the freeway, and you see a car stop in front of you, and you need to slow down and stop, or else you're going to crash. So this problem is going to ask, what is the stopping distance? Say this is like, this is actual like things car manufacturers deal with. Say they input a value, they say our car can only stop this fast with this amount of acceleration. How much space do we have? And that goes to like, the DMV, and they say like, oh, you have to be this many car lengths away from a car in front of you. So, what is the car's stopping distance, and how long will it take for you to stop? All right, let's draw the problem. I always start out with a nice picture or of some kind. I don't want to draw a car, so I'm just going to draw a dot. Let's go like this. So we have an initial velocity going that way. What is the final velocity? So they don't give us any other numbers. We have initial, and we have that 5. This is where, the word problems of physics sort of seep into your understanding. You need to sort of see what the problem's asking. So we want to come all the way to a stop. What's our final velocity? 0. So let me put the values in. So initial velocity, right when we're going, that is 30 meters per second. And our final velocity is, you guys got it? 0 meters per second. Okay, just from reasoning, we found another variable. Okay, we're going to be stopping at a consistent rate. So typically that means we are changing our velocity. That 5 meters per second is the acceleration. So I'll put over here. Should it be positive or negative? Negative. Also, if you're not quite sure about the wording, you can look at the units. Acceleration is always meters per second squared. So we have acceleration, we have initial and final velocity. We can pretty much start using some of those kinematic equations to solve for these things. Let's start at the first one. Which equation should we use? The third one. Can you read it out loud? Or, third one says, I think that was the vx squared all right. Does this look good to everyone? Also, like I listed like 4 or 5 of them. They don't have a specific name or a specific order. So even though on my list, this was the third one, that's not going to be the same on everyone's list on like the internet or in other books. What can I solve with this equation? What can I find? So I know final velocity, I know the initial velocity, and I know the acceleration. The only thing that's unknown in this equation is the position, or the displacement. So this equation, I can manipulate, I can sort of, change it around. So I'm going to take this equation, and let's solve for x, or the displacement. So what I mean by that is I'm just going to have the displacement on one side, I'm going to have all the other terms on the other side. Okay, so if I want to put everything else on one side, we could say this is Vx squared minus x squared. And is that going to be it? What's the rest of it? Yeah, I heard it. So divided by 2a. All right. So doing this before I plug values in makes my life easier, because now I just need to do that. And whatever comes out the other end is my result that I need. So if you can, try to change the equation around before inserting values. I don't have, or actually let me write it out. Do I have them? Okay, yeah. Yeah. So let me put in the values. Final velocity is 0. The initial velocity is 30. And these are both squared. All of that over 2 times the acceleration. Okay. If anyone has a calculator, that would be great. So what do we have? We have 900 over negative 900 over 10.
What's 90?
So 90, right. And we have a negative over a negative. So our final answer is positive. 90 meters. All right, so that's the first question. And now here's the other thing. You're trying to flex our math and physics muscles, is that as soon as I find one part of the question, and none of the other terms change, it says like, oh, now it's traveling at this speed. Once I find one value, I now have that fourth term. I can use the more robust form of that kinematic equation. So sometimes you need to solve, you need to sort of like, it's like a maze. You need to snake your way around, find the easy term, the easy variable. Okay, I found the displacement. And now I can use that displacement along with the velocities and the acceleration, use all of them together to find the time. So now which form should I use for the time? One did I use? So now since I have so many variables, I can use the easiest one. Whatever I find to be the easiest at the moment. The first one, right? Okay. Plus E plus okay. I should be having an X on these, but that'll be more important in the next chapter. Making sure you always label. Okay. So now in this form, what are we solving for? We're solving for time. That's the only thing we don't know. So, easiest way, arrange the equation. Oh, sorry. Okay, delta t equals over, hey, very straightforward on this one. And then let's see if we could do that. So it's going to be 0 minus, 0 minus the initial velocity is 30. Over A. Oh, sorry. Minus 5. Okay, I can't have a minus time. Okay. So, minus 30, or negative 30, over negative 5. Final result. 6 seconds. Yeah. All right, awesome. So, every, this is like a fourth of all problems. Not just in this class, I mean like everywhere. Okay. Next up, we are going to talk about free-falling objects. Okay, so talk about things moving left, right, acceleration, or you in your car, it's steadily accelerating, you're getting faster and faster. I've also brought up things about gravity. Me tossing a ball up in the air. Gravity is affecting it somehow and making it come back down. But how can I actually use this acceleration, when this is a tennis ball and this is a heavy metal clamp, it's got a different shape, it's a different weight, this is much lighter, smaller. Does the size, shape, weight of an object matter? Does a heavier object fall faster than a light object? If you think the heavy object falls faster, then you raise your hand if you think so. It's okay if you think so. If you think a light object might fall faster, raise your hand. If you think they're the same, we only have 4 people in the class. Okay, yes. So this is something that's brought up a lot. It's something that you've probably already seen, but it's worth talking about because how can I predict the motion of things when all things are going to be different? Different size, shape, mass, weight. It's like me, looking at these two, tennis ball, paper towel, I should expect them to hit the floor at the same time, right? Why don't they? What's that?
I'm guessing with the napkin free fall.
That's pretty much on the right track, yeah. It's something, something extra is happening here. I'm, expecting this. Gravity should work the same on, everything. It's pulling everything down to the ground. Does that mean it's actually pulling the heavy things faster? Not necessarily. This is something that was brought up by Galileo. I'll just put his picture up. So we have every object near the Earth, something that he sort of reasoned out and sort of, held his ground defending, that every object will fall every object will fall at the same acceleration. And so I have this little thing here that's sort of like my tennis ball and paper towel example. I have a piece of paper, there's a feather, and a penny inside of this tube. When I flip it over, the penny hits the bottom way before the other two. And we don't have a sort of like room size one. I can't use any big objects. I'm going to try to use this. Actually, I'll do this at the end. Maybe it won't work. Then I'll have wasted a bunch of time. So I'll do that at the end. Do all the demos at the end. That sounds better. We have this sort of example of things falling at the same rate. Now, this is sort of what's brought in the sort of creative freedom for Newton to work. Newton saw that, I think the story is an apple fell on his head one day. He said, "Oh, this thing is accelerating because of Galileo's reasoning, and this," and then he was sort of like scratching his head, and then he saw the moon in the sky while sort of sitting in the afternoon. And then he said, "Why isn't the moon, crashing down into the Earth?" So it's also accelerating at the same rate towards the Earth. And we'll get on more about Newton in the next chapter. 2 more chapters. But as for right now, the acceleration on every object is just acceleration. So in all of those kinematic equations I brought up before, wherever it said A, you can always replace it with negative G, because we're always calling down negative, and G is 9.81 meters per second squared. Okay. Let's see, what else? I think that's it. You know, let me try it. Otherwise, I'll forget. Okay, so I have sucked out a large portion of the air in this tube. And now let's try that same exact thing. So Penny was like dramatically like ahead of everything else. So see, maybe if I suck that to the air. Still a little bit of air in that. So the reason the things that are, seem lighter, oh, they're just falling slower. The reasoning is that there's just air molecules in the way. It has to push out the air molecules. And the paper has a large surface area. So the paper has to sort of like weave past. Have you ever dropped a paper? It just sort of like rocks back and forth. It has to sort of slip past all the air molecules. That's pretty good. There we go. All right, that's enough. That. We get onto, the usefulness of that is now we don't have to find the acceleration of a penny. It's slightly different than the acceleration of a feather, or this clamp versus a tennis ball versus a baseball. We could say that everything on Earth is affected by a constant acceleration downward. So that means everywhere on Earth, we will be using kinematic equations to find out where things are. So we have this example of, on graduation, a student throws their cap in the air. I know how much graduation gowns and stuff are. I don't know why you do that. But you throw your cap in the air. Let's say it goes straight up and straight back down. How long does it take to reach the top? How high up does it go? And then, how long does the entire process take? So, start out the way I always like to start out. We're going to do a little picture. This, it's just a dot and throwing something straight up in the air. Some positive velocity upward. All right. I will fill in equals 14. That's a bad spot. Let me. So that's right as it leaves my hand. So I'm throwing it up in the air. Right as it leaves my hand, that's the fastest it's going to be traveling upwards. Then it will reach a point up in the air, up at the top. This is like, now that you kind of see it, it's the exact same thing as that car braking example. Now the acceleration is just downward. So what's the velocity up here, right at the top of this sort of toss? 0. Let me make more room. Okay. And we know that the acceleration is constantly downward, constantly pointing downward. Say minus 9.8 minus 9.8 meters per second squared. So it's the same exact thing. Starting out, we just look at what we want to find. First one, how long does it take? So we want to find time, and we have 3 variables. That means we're going to use the form so I'm going to write it out like this, because that's the way I've written it before. But then when we plug in the values, remember this is going to be negative. All right. Solving for time. Just going to jump straight to it. So we have the final velocity is 0. Come on. 0 meters per second. All right, much more complicated fraction here. Let's see, did I already do it? Minus, yes. So I get 50. What will this be? What units? We're solving for time, so this is seconds, right? All right, first one done. And now, going forward through the second and third part, we have the time it takes for it to go all the way up. Now, what's the distance to the highest point? Same exact thing. We're looking for a displacement. So let's use a different form. Yeah, we'll use that one. Or does anyone have, we could use, what would someone use to find the displacement now? Which one? So like, you just say like first one, second one, third one. I can look it up. Third? Okay, we can use the third one. Okay, I'm trying to run out of room. Okay. And we've already seen where this one goes. We're solving for the displacement. We've already seen how to solve for that. Let's try to keep these from overlapping. So I'm going to go all right. Squared minus initial velocity, 14.7. Okay. I can't do that squared. So ultimately we will get, yeah, I don't have any of the middle steps of this. Does anyone have it before I write it? Think you have it? How much? 11? Yes. $11 meters. That's a pretty good toss. So that's probably, yeah, that's taller than the McLean building. That might actually be as tall as, maybe almost as tall as the engineering building. Yeah. Okay, next, last part. I wish the slides were like long instead of wide. Okay, last part. Assume the cap is caught at this. Yeah.
I was just a little confused. Before you wrote that A is equal to negative G.
Yeah.
So is G equal to negative 9.8?
G is equal to negative 9.8. Yes. Yeah. Right. So some forms might already have a G, written into it, and it's typically they're just saying we're using the acceleration of gravity, and the acceleration is downward. So whenever we see those value signs, positive, negative, they're just sort of directions, down or up, or left or right. And so eventually they'll help us, do these equations, but initially they're just sort of marking directions. All right, and the last one. So we can do, we've already found the time that go from 1 point and up. We can then find the time it takes to go from the top down. But I'll say the sort of shortcuts way in this one, since I'm running out of time, is that since it's thrown and caught at the same exact height, the sort of the arc it takes will be half going up and half going down. So it's going to, acceleration doesn't stop, change, or, how do I phrase this? the acceleration is constant at the same rate, and so the time is doubled going up and then back down. I think that's good. So, but I think you can maybe see if it wasn't so exact, I would then just go from the top and then back down as far as the problem says. Say I throw the cap up and it lands on a ledge somewhere up there. It goes up, and then someone comes in with a ledge, lands on the ledge. It's a different distance. So then I just have that, it's a more complex problem, maybe for a test. But we kind of have the steps we need to solve this. I'm just going to say right here, 1.5. If you want to maybe go over this last part, maybe I could do a more complex example. If you want, we could go out after class or in my office hours, see an example like that. But with that, I think we are on to the next chapter. Yeah, awesome. Okay, I'm going to start out with this, and then we will continue from this next slide that I'll go over. So that way we're in a good spot for the quiz day. By the way, Thursday is a quiz, so it'll be on all the material up to this point. So on the 2 homeworks. So just heavily on unit conversions, vectors, and I'm going to say a little bit of motion. Since I just finished today, I'm not going to have the whole thing on motion. But basically, think of it as whatever was on the 2 homeworks, generally on the quiz. More on the quiz is no notes. It's just whatever you can sort of maintain in your head. If there's a complex equation, maybe I think it's too much to remember, I will give it to you. Otherwise, that's the quiz on Thursday. Motion in 2 dimensions is something that I could have just bundled this together when I was going over motion just right now, because it is almost that simple. I do need to go over the sort of official wording. Now we have position vectors. So instead of things moving in a straight line, think of a number line, left, right, or up, down. Now we are getting into more real world examples. So, for instance, let's see, we are on, say for example, I have a obscure arc. This is not a graph that we've done before. This is a Cartesian 2-dimensional graph with 2 positions. So this is later on we'll say, how far is that projectile gone, or things moving left, right, and up and down. Now imagine this case. You're looking at the side view of me throwing a ball or something. That's the blue arc. So it's just like a side view, side slice. And I want to find the position of that ball, that football, whatever, right here. Now it's a little bit more complex than our previous problems. We need to find that position vector, R. And R is just a piece. It has components, horizontal and vertical. This is going to be so familiar to you since we've gone over vectors in the beginning of the class. You may have seen this form before. X, I hat. Right. Okay. So we have that arc. That's one position vector going straight to the baseball, whatever. I throw it. I take a picture, and I get that position vector. Okay, I got it. It's perfect. I know exactly where it is. But then you imagine the time keeps rolling. That ball is going to move somewhere else, and now we have this big headache because we have to find another position vector. So we found that one. Then after some time, the ball moves over here. Now we have to find that one. Pretty much, this is kind of reminiscent of what we've done with vectors in the beginning. So I'm just going to take the difference of the two. Let's say this line right here is delta R. These should be vectors. And yeah, this is a x, y graph. All right, so I will talk more about motion in 2 dimensions next time, and then we're gonna go over like projectiles. I'm gonna have a thing, I'm gonna have a cart, a ball, and yeah. So make sure you finish your homework before Thursday midnight. It will help you study for this quiz next time.
The quiz online?
What's that?
Quiz online?
Quiz is in here.
Besides the other classes?
Yeah. Yeah.